cryptanalysis. The first talk is on key recovery attacks onto Kravatte. The co-authors are Roland Chenio, Thomas Fur, Henri Schiffer, Jean Gros, Jean-René Reinhardt, and Ling Song. And Jean-René is the speaker.
Thank you for the introduction. So we are going to present here recovery attacks on full Kravatte, on primitive versions of Kravatte. We've already seen this morning the file construction. Well, it's enabled to give variable input lengths and output lengths peer-read from a permutation. And it can be used directly as a map, with a long input, short output, or a stream cipher, short input, an IB, and a long output, a keystream. And in various modes also. So we'll be interested, there have been several versions that have been proposed, and we'll be focusing this talk on the ePrint version that was posted last year in July, and the ECC version, which was outlined at ECC in November. So the security claim for all these versions is that we have 256 bits of security as long as the number of input and output block processed is lower than 2 to the 137. So this is the outline of the schematics for Kravatte, which is the Ketchak-based instantiation of Farfal. So we have after some key schedule that derives an input key block and an output key block. After that, we have 3 phases, the compression phases, which turns a certain amount of input blocks into an accumulator state. Then a middle phase that turns this accumulator state into a rolling state. And finally, an expansion phase, which diversifies these output states. We go through a permutation, and in the expansion phase, we XOR with the output block, and we get to the outputs. So the number of Ketchak P rounds in each stage can be different. In the ePrint version, we had 4 rounds here and here, and in the ECC version, and the final version also, we have 6 rounds here and here. So, quick reminder on the Ketchak run function. So we have states that are 1600 bits. That can have some kind of parallelepiped representation. You start by, You start by a linear diffusion layer, then you have 2 linear bit permutation layer, and you have only one non-linear layer, the key layer, which has degree 2 in the forward sense and degree 3 in the backward sense. And you have also some constant addition here, which is affine. So we are going to present attacks against Kravatte. One attack that abuses a property of the compression phase, and higher order differential attack, and 2 attacks that focus on the expansion phase of Kravatte, meeting the middle algebraic attack, and linear recurrence attack. So all these attacks recover the output key block, and they have complexities that are lower than the security claim. The best attack being the linear recurrence attack. So let's start with the higher order differential attack. The main observations that was already noted by the designers is that it's easy to build an affine space of values in the accumulator state here. You just have to consider 2 to the n block messages with n blocks, and that are chosen, each block is chosen among 2 possible values. And if you have this property of being chosen among 2 possible values, it's also here. You also can have only 2 values here and 2 values here. And when you XOR all these values, you get an affine space. And the dimension of this affine space will be the number of blocks with high probability, as long as the number of blocks is lower than the size of the state. So we can use this to build a distinguisher on the beginning of the, well, on the beginning of what you get when you consider the middle phase and the expansion phase. You have the accumulative state, and you have to perform some partial termination where you apply the whole middle permutation and some parts, some beginning, the start of the expansion permutation. So you cover air rounds of Kravatte, and each intermediate value here is a function of degree 2 PR in the bits of the accumulator state. So it's well known that when you sum a value, the images of a function over an affine space, you are in fact differentiating the function m times, if m is the dimension of the affine space. And if the dimension is larger than the degree, then the derivative will be 0. And this will give equations that are satisfied by the intermediate states independently of what happened during the compression function, and in particular independently of the input p. So if the dimension is large enough, then you have a distinguisher on the intermediate state of the expansion layer. So then you can use this distinguisher to on key recovery attacks by performing last epsilon round attacks, where epsilon is the number of remaining rounds. So the idea is to express the intermediate state values as a function of the outputs and the output key block, and combine these expressions using the higher order distinguisher in order to get equations on the K out block. And if you consider outputs that are large enough, for each output block you get one block of equation. So if you consider outputs that are large enough, you collect enough equations to solve the system and recover the output key K out. So we can consider what happens when we have just one final round. So in this case, the function f has degree 128, and we have to use structures of 129 blocks. A remark is that we can the distinguisher also applies, continues to apply after the beginning, the linear beginning of the K-Chakri round. So in the analysis of the last round, you only have to consider what happens up till the inversion of the key layer, and after that, well, it's covered by the distinguisher. So when you look at this, you see that all operations are performed independently on every row and every S box. So you can solve this system row by row, S box by S box, and recover K out by chunks of 5 bits, a kind of exhaustive search, and the complexity of this attack will be on the order of 2 to the 136 as well in time and in data. So it's already lower, a little bit lower than the Segretti claim. So this was experimentally verified on a round-reduced version of Kravatte. We can do a little bit better by considering two end rounds. So now the function f has degree 64, and we consider 65 messages, block messages for the structure. And we are going to express the inversion of K out and the output, so the output algebraically, and write down this equation, this algebraic equation, and solve them by linearization. So all the monomials that appear in these expressions will be considered as fresh variable, and we solve the linear systems that results. So normally, it's a function of degree 9. Normally, you would have to consider all the variables of the 1600 unknowns bits of K out and of degree 9, but we can do better by looking at what happens in the inversion of two rounds. So the main remark is that the outer key -1 layer can only form 20 monomials. Yes, for each p minus 1. For each S box, you only form 20 monomials per S box. So globally, you have on the whole state only 2 to the 13 monomials at this stage. So the linear layer, linear diffusion layer theta will break locality. So at this stage, every bit is a linear combination of all these monomials. And then you have here finally the internal p minus 1 layer, which is of degree 3. So you only form monomials that can be obtained as the product of up to 3 monomials that we have here. So globally, you have 2 to the 36 possible monomials, which is far lower than the total number of degree 9 monomials. And well, this can be used to solve the system. This results in following complexity for the attack, for the last 2 rounds attacks. So yeah, for the e-print version of Kravatte, with data complexity that is far lower than the one claimed in the security claim. So let's now move to the expansion phase attacks. So the main observation for these 2 attacks is that well, the expansion phase is in fact a stream cipher, and we can study the security of the stream cipher independently of what happened in the compression phase and what happened in the linear phase. In particular, it's a really particular stream cipher since it's a linear registered filtered by permutation. So we have 2 attacks against the expansion phase. The first one is the kind of meet-in-the-middle algebraic attack. So the idea is to consider the accumulator state as an unknown, and also the key out as an unknown. So you have 2 unknowns here and here. And to remark that since the rolling function that diversifies the rolling state is linear, the complexity of these blocks in the X in the rolling state is not they are pretty much equivalent to the rolling state, and we can form algebraic equations by equating the expression of this intermediate state as a function of X of the rolling state, and as a function of the output and the key block. So you have equation like this. So if we split the expansion, if we split the expansion phase permutation in 2 forward rounds and 2 end rounds, 2 start rounds and 2 end rounds, you have equations like this, and you get such an equation for every output block. And so if you collect enough of them, you can solve again by linearization. So the number of monomials is quite limited. So we already saw that we can limit how we can compute the number of monomials in K out in this stage. The number of monomials that we form in the beginning is just the total number of monomials that we have in 1600 variables and degree 4 and of degree less than 4. So this leads to attacks with a really low data complexity. We can do even better than that by considering LFSR cryptanalysis techniques that were developed by Key, Wongjum, Elset, and Wang. Starting from the rolling state register, it's a linear recurrence register. So it is updated linearly through a matrix L, rolling state update matrix. And in fact, the values that are the sequence of values taken by the rolling state is a linear recurrence sequence. So quick reminder, if you consider a polynomial P and a sequence U, you can form a sequence P.U by considering, whose ith term is the linear combination of terms of U starting from Ui, and the linear combination is given by the coefficients of P. And so we say that P, the polynomial P, annihilates the sequence U if P.U is identically 0 if each term, every term here is 0. And if such a polynomial exists, U is called the linear recurrence sequence. So it's pretty straightforward to see that the sequence of xi is a linear recurrence sequence. If you apply any polynomial p on the rolling state, you can derive such an expression. So the ith term is simply L to the power I times p applied to the matrix L times the initial value. And if p is an annihilator of the matrix L, then this is 0 for every value of I. A remark, this is also true for any linear combination that you can form of bits of xi. So, yeah. If you consider a fixed linear combination, you can just factor out the linear mask, and you get again that it's 0 equals 0. So now let's move to what happens when you filter your linear register. Well, in fact, everything can be adapted if you consider the monomial state. So it's the state, it's a vector containing all the monomials of degree less than d being the degree of the function. This monomial is still linearly updated. It's pretty straightforward to see this with a larger matrix, obviously. And as a consequence, it is also a linear recurrence sequence for any polynomial that cancels the monomial update matrix. And this is a distinguisher on, this is true for the monomial state, but also for any combination, linear combination, fixed linear combination of the monomial state, and in particular for the sequence of the intermediate states that we get on one branch after n rounds of ketchup. So this is a distinguisher, and we can take the last round attacks framework that was developed for higher order attacks and just replace the higher order distinguisher by this linear recurrence distinguisher to get attacks that use this distinguisher. And the equations will be like this, and the complexity of the attack will depend on the degree of the polynomial cancelling these sequences. So you just have to look at this, and in fact we can here exploit another specificity of Kravatte, which is that the rolling function only affects one plane of the K-check state. So only 320 bits are affected by the rolling function, and the other part of the state is left unchanged. So if you consider the update matrix M, that is the restriction of the update of the rolling function to this last plane, and you consider the corresponding monomial update matrix restricted to the last plane M, well, if you consider the characteristic polynomial of this matrix, it cancels all the sequences of the monomials involving the last plane, and the other monomials which involve only the bits of the other planes are constants, and so they are cancelled by the polynomial x plus 1. So if you take the product of these two polynomials, you have to get a polynomial that cancels every monomials. And the degree of this polynomial is the number of monomials of degree less than d in 320 variables. This polynomial can be computed using a fast multiplication algorithm of Schematics by using the rich algebraic structure of the matrix MD. And we have performed this computation in the case of two rounds, so U4 function. But and here are the figures of the degree and the time required to compute the polynomial for larger functions. So this linear distinguisher can be used to attack the April version with one last round attacks in these complexities, and it even enables to attack the ECC version by considering a distinguisher on 4 rounds and 2 last round attack. So some concluding remarks. We have proposed several attacks against the preliminary versions of Kravatte. All these attacks exploit the fact that we have a really low algebraic degree for key and key -1, and the ability that we have to bypass some part of the construction of Kravatte. There are two specific points in Farfal, the convergence point, which can be abused in the higher order attacks, and the divergence point that can be abused in the meeting the middle and linear recurrence attacks. So following our results, the designer tweaked their design, and it was presented this morning. So they increased the number of runs compared to the previous version to 6. So this enabled to resist the higher order attacks, and also they made the rolling function in the expansion phase non-linear, which avoids the linear recurrence attacks. So thank you for your attention.
It's time for a very quick question. No thanks for me again.